Hello physics students, this is Dr. Brenzy here, and we are on lesson 2.1.3. This is video number 2, and this lesson is going to be about using free body diagrams in Newton's second law to calculate force or acceleration in two dimensions. I know it says and there, but it should really be or. So what I want you to do, since we are not actually in class to stop and jot, I just want you to think for a minute. How do you think we might find the tension in these two cables A and B? Just pause the video for a minute, come up with some ideas, and when you have an idea, unpause the video and we'll proceed together. Okay, well, now that you've had your brain warmed up with this problem, what we do when we have second law problems in two dimensions is that we treat them very similarly to laws in one dimension, except when you write your force equals mass times acceleration, you need to break it down into its x and its y components. If you remember back in Unit 1, when we had motion, projectile motion, in two dimensions, you might remember the thing we did is we broke these things down into x and y components, and then we had equations for just the x motion, which was this way and that way, and we had equations for the y component, which was motion up and down. We're going to do the same thing with Newton's second law in two dimensions. We're going to consider the horizontal direction separately from the vertical direction. So let's see what that looks like for this problem that we just wrote down. Oh, I noticed that I already put something up here. Oh no. So let me erase all the stuff that I wrote down here. Okay. So what we'll do in this case is that we'll write our net force equals mass times acceleration for horizontal motion, and we'll also write a separate equation for vertical motion. So we'll have two different sets of problems, or not problems, but two sets of equations to work with. So let's go ahead and apply this to the example that I just showed you in the little stop and jot. So let's go ahead and try to find the tension in these two strings. I think I called them cables in the stop and jot, but same principle. So I'm going to call this one rope A, or string A, and we're going to call this one rope B. And hanging from these two strings, we have the string coming out horizontally, we have the string coming out at an angle of 50 degrees with respect to this ceiling, and those two come together, and hanging from those is a ball that has a mass of 15 kilograms. So the first thing I want to do is I want to go ahead and start drawing a free body diagram. Well, there are three forces acting on this ball right here. We have the tension due to rope B. It's at an angle of 50 degrees. So I am going to include this little angle in my free body diagram just to remind me. And then I also have the tension due to rope A. And notice that I put a negative sign on here. I'm going to go ahead and put a negative sign in here. I'm going to assume that all my forces are going to have a positive value. Okay? And so when I take into consideration direction, I'm going to write that negative sign right there. And then I have the gravitational force, which is working down. Now there was some confusion the other day about, hey Dr. Brenzy, when do I multiply this times g, little g, the force due to gravity? Well, here's a way to figure it out. We know that the force due to gravity is mass times the acceleration due to gravity. Well, what am I being given over here? Am I being given a force due to gravity, or am I being given a mass? Well, kilograms is a measure of mass, So I know that I need to convert this into newtons by multiplying times the force due to gravity, or acceleration due to gravity, excuse me, little g. And so I know that now, in this particular case, I have to multiply 15 times negative 9.8 to get the force due to gravity in newtons. And in common terms, we would call this our weight. So the weight of this ball is 147 newtons. The second thing I'm going to do is find the force x and y components. So what I'm going to do is I have a force, this tension force right here, that is not along the vertical direction and it's not along the horizontal direction. It has components in both directions. So I want to break this force down into its x and y components. So I'm going to go ahead and draw that force in a separate little diagram here. It's not a force body diagram. But what I'm going to do from it is make a triangle, a right triangle. And since my angle is down here near the mass, my opposite side has to be the sine, because sine is opposite over hypotenuse. So I'm going to write f sub b sine 50 degrees. Now, how could I check to make sure that I have the correct trig function here? Like, what if I often get sine and cosine mixed up and I don't remember which one to put here? Well, I can ask myself, okay, opposite over hypotenuse gives me what? It gives me sine. So if I take this divided by this, I should get sine of 50 degrees. So that's a useful little check you can do. Well, what does the other one have to be, this one down here? Well, that's adjacent over hypotenuse. So the adjacent side has to equal the hypotenuse times 50 degrees. Okay, now that I've split this force into its x and its y components, I can go ahead and start redrawing my force body diagram. And I've already written my negative FA, force due to rope A. I have the force due to gravity is negative 147 newtons, that didn't change. And now I'm going to write both of my components, my y component and my x component, on this force body diagram. Now I have all of my forces either up and down or left and right. Okay? So now that I have all those forces either up and down or left and right, I can go ahead and, and I'm just going to redraw that, so you don't have to redraw it, but I do because I'm on a new slide. But we're doing the same problem, so you don't have to redraw this, you don't have to redraw that. Okay, so now that I've done that, the third step is to write the second law for both directions. So I'm going to create my little x and y table, and I'm going to go ahead and write F net equals ma for the x direction, and I'm going to go ahead and do the same for the y direction. The x direction is these two forces right here, this one and this one. Oh, and I forgot a negative FA on my little diagram there. Oops. But I did remember it over here. So let me quickly put that in there in my diagram. Okay, so the sum of these two forces, 1, 2, has to equal mass times my acceleration in my x direction. Well, is this ball changing velocity in the x direction? No, it's not. So my acceleration has to be 0. Which means mass times acceleration is 0. Now let's turn our attention to the y direction. These forces right here. And the sum of those forces, negative 147 plus f sub b sine 50 degrees equals the acceleration, the change in velocity of this ball in the y direction. Well, is this ball changing velocity up or down? No, it's not. It is staying still. So my acceleration in the y direction is 0. Alright. Now, let's take a look at what we have here for equations. I have an equation that has two variables over here. So it doesn't look like I'm going to get a single tension or the value of either of those forces from that. Over here it looks like I just have one variable to solve for. So I'm going to shift my attention to this equation over here and solve it for f sub b. Okay, well, in order to solve for f sub b, I have to undo PEMDAS. You might remember PEMDAS is your order of operations, parentheses, exponents, multiplication, division, addition, subtraction. But when you solve equations, you undo that. You do it in the opposite order. So I have to take care of undoing subtraction and addition first. So let's undo that subtraction by adding, oops, actually what I did first, I just figured out what sine of 50 degrees is. And that's 0.766. And then I'm going to go ahead and add 147 to both sides. And when I do that, I'm left with 0.766 f sub b equals 147. Now I have to undo multiplication and division. So I have to undo this multiplication next to the f sub b, and I divide by 0.766. When I do that, I'm left with f sub b equals 191.9. But when I go to report this f sub b, I need to have two significant figures because that's what the mass has, two significant figures. So I'm going to report that as 190 newtons. Now, actually, I've shown you what I'm going to do next with this. What I'm going to do next with this is now I am going to plug that into this equation right here. So I've replaced f sub b with 191.9. Notice I didn't replace it with 190, which is the value when it's rounded to its significant figures. I'm going to plug in the one that has more than enough significant figures. That way I don't introduce any extra rounding error when I evaluate what f sub a is. So I've plugged in 191.9, and now I have to multiply that by 0.642. When I do that, I get negative f sub a plus 123.4 equals 0. Subtract 123.4 from both sides, and I get negative f sub a equals negative 123.4, which means f sub a equals 123.4. But since my mass has two significant figures, my force also has to have two significant figures, so I would report that it has a force of 120 newtons. Okay, wow, that took a lot of work, didn't it? You did, but I know that you're capable of doing this. I know that you're smart enough of doing this. We just need to learn how to persevere in solving tough problems. And we're going to get plenty of practice in doing this so that when we go to take the formative, we are totally knocking this out of the ballpark and rocking it. Now let's even go to a tougher problem here. So this is another example here. So now I have two strings, and neither of them has along the x-axis or the y-axis. So I want you to kind of think, what do you think this is going to involve? Am I just going to be breaking down one force into x and y components? No, hopefully you recognize that now I have to break down both of these forces, both of these tensions into x and y components. So let's go ahead and get started with that. So let's draw a free body diagram. And we know that, oh, by the way, I forgot to tell you that this ball has a weight of 140 newtons. So let's draw the force of gravity pointing down for a free body diagram. Now, am I being given a weight in newtons, or am I being given a mass in kilograms? This time I'm being given a weight in newtons. If I'm being given a weight in newtons, I don't need to convert it to newtons. It already is in newtons, so I don't need to multiply by anything. I can just write the force of gravity is negative 140 newtons. No multiplication needed. So let's go ahead and label these ropes. Rope A, rope B, and then write their tension forces. Okay. So this is the tension force of rope A. It's inclined at a 45-degree angle, and force of tension, the tension in rope B is also 45 degrees off of horizontal. Alright, now that we have a free body diagram, we're going to have to split the forces into their components, X and Y. So, for the force in rope A, my Y component is F of A sine of 45, but you'll notice that the component of rope, the X component, is negative FA cosine of 45. It's in the negative direction, so I'm going to write negative. Okay, so be careful about that. For the rope and the tension due to rope B, split it into its X and Y components. This tension force is positive X or positive Y direction. This tension force is positive X direction, so both of those have a positive sign out in front of them. Alright. Now let's rewrite our free body diagram with our force components. So in this direction I have the force of gravity, negative 140 newtons. The only force that I have in the negative X direction is this part right here, so that goes right there. The tension force is Y component from rope A goes right there. So basically I've now written the force for rope A in its components here and here. And now let's go ahead and write out the tension of force B as its components. And when I do, I'm going to get F sub B cosine 45 pointing in the positive X direction. And I have a second force going in the positive Y direction, since both of these are positive Y forces, this one and this one. So I'm simply going to just write plus F sub B sine 45 degrees. Alright. So this would be my force body diagram split into components. All of the forces are either horizontal, X, or vertical, Y. Alright, now I'm going to rewrite this. You don't need to because you have paper, I have slides, so I have to rewrite some stuff. Okay, and you already have this diagram. Oops. You already have this diagram and this diagram, so you don't need to rewrite these. But our third step is to write out Newton's second law for each direction. So let's create our new X and Y table. And write out our equations. F net equals MA. F net equals MA. And now, let's remind ourselves that X is the horizontal direction, Y is the vertical direction. So, my two horizontal forces are negative FA cosine 45 and F sub B cosine 45. So I add those two up together, and I need to set those to mass times acceleration. Well, the acceleration in the X direction is 0, because I'm assuming that this ball is not changing velocity. So let's set that equal to 0. And for the Y direction, I have to add these forces and this force and set those equal to mass times acceleration in the Y direction. Well, is my velocity changing in the Y direction? No, it's not. So I'm going to set the acceleration equal to 0. Now let's kind of take a step back and look at these equations here. This looks like a bigger mess than what I had in the previous problem, isn't it? Because it looks like I have an equation with two variables, and I have a second equation also with two variables. So there isn't one particular equation I can solve and get a tension force right away. So what do? Well, this is where your practice in Algebra 2 with solving systems of equations comes into play. We're going to solve this system of equations by using what's called the method of substitution. What I'm going to do is I'm going to find the force I'm going to solve this equation for one of these forces. I think I'm going to solve it for the force in rope B. So let's go ahead and do that. Now the reason I picked this one over here is because it looks a little bit easier than this one over here, because this one has this extra constant. So that's why I chose to solve this one over here. So what I'm going to do to solve this for f sub b is that I am going to write out, I'm going to add f sub a cosine 45 to both sides of the equation. And when I do that, I will get rid of this term on this side of the equation. And when I do that, I'm left with this term, f sub b cosine 45 degrees. And on the other side of the equal sign, I now have positive f sub a cosine 45. That's what I added here, but I didn't have enough room to write it, so my apologies. Now, if I divide both sides by cosine of 45 degrees to get rid of this factor in front of, or with the f sub b, it turns out that f sub b equals f sub a. All these cosine 45s, they happen to just divide out. Now, does that happen every time? No, but it does happen for this particular example. So, f sub b equals f sub a. In other words, the tension forces in both ropes are equal. Now, you might have actually realized that just by looking at this diagram. I mean, it's symmetric, right? So, of course, these forces would have to be equal in order to preserve that symmetry between these two things. It shouldn't matter which rope I call A and which one B, because they're both at the same angle, so they better both have the same tension. Well, what is that tension? How can I figure that out? Well, what I can do is I can take this equation, f sub a equals f sub a, and go over here, and everywhere I see an f sub b, I'm going to substitute the other side of this equation, which is f sub a. So, let's do that. And by the way, as I'm doing that, I'm also going to figure out what sine of 45 degrees is, and it happens to be root 2 over 2. So I'm kind of doing two steps at once there. So root 2 over 2 times f sub a plus, now here's the point where I find f sub b, so I'm going to replace it with what's on this side of the equal sign, which is f sub a. So now I have root 2 over 2 times f sub a. Minus 140 equals 0. Now, when I add these two like terms together, they're both like terms because they both are of f sub a, and they both to the first power, so they're like terms. When I add those two together, root 2 over 2 plus root 2 over 2 equals root 2. So I have root 2 fa minus 140 equals 0. Now I can solve for f sub a. Add 140 to both sides. I have root 2 f sub a equals 140. And then I have to divide by root 2. And when I do that, I get 140 divided by root 2, which is rounded to 100.0. But since my weight was reported to two significant figures, I have to round that also to two significant figures, which is 100. It looks like one significant figure, doesn't it? So more accurately, what I would do is I'd actually convert this to scientific notation, and now I'd write 1.0, because this has two significant figures, times 10 to the 2 newtons. And that's why scientific notation is nice, because you avoid this little, is it one significant figure or two significant figures? If you put it in scientific notation, this term out here tells you the number of significant figures you have. In this case, it's 2. Alright. Okay, so what do I do with this? Because I still have to find f sub b. Well, f sub b equals f sub a, right? So I can take this f sub a, bring it over here, and plug in its value. Now, for this one, it's pretty trivial, because f sub b has to equal f sub a, so f sub b is also 100 newtons. Okay, so there we go. We figured out what the tension in both of these ropes is. Okay, again, a pretty long, hairy process, but if you kind of remember that I got to do this step, and then I have to do this step, and then I have to do this step, then it's not so terrible. You know, we just need to keep practicing, just like you have to practice any other tough problems, and we're going to end up persevering and being able to solve these types of problems. Alright, physics students, hope you found this video helpful, and I look forward to seeing you in class soon. Bye.